Most of the universe is a ghost, an invisible skeleton holding everything together. This cosmic dark matter web dictates how galaxies move and cluster, yet it emits no light and has never been seen directly. In fact, over 85% of all matter in the cosmos is this mysterious dark substance, making its detection one of science's most profound challenges. By the end of this exploration, you will understand how we are finally creating detailed maps of this hidden architecture. What cosmic secrets are encoded in the empty voids between galaxies, and what does this dark framework reveal about our own ultimate fate? What does it feel like to realize we live in a universe mostly made of something we cannot see? Our universe has a hidden architecture, a framework of immense gravity that dictates the placement of every galaxy. This structure is the cosmic web, and for a long time we could only perceive its shadow. Scientists first began to suspect its existence not by seeing it, but by noticing the strange behavior of things we can see. Spiral galaxies, for instance, spin at such tremendous speeds that the gravity from their visible stars alone should not be enough to hold them together. They should fly apart, their stars scattering into the void, yet they do not. Something invisible, something with immense mass, must be providing the extra gravitational glue to keep them intact. This was our first major clue to the dark matter saturating the cosmos. The same gravitational mystery appeared within gigantic clusters of galaxies. These clusters move with speeds that, again, defy the pull of their visible matter. There simply is not enough luminous stuff to account for the fierce gravitational forces at play. It is as if you watched a group of children on a playground, all seemingly swinging and sliding on their own, but their movements are perfectly synchronized, pulled by the strings of some unseen puppeteer. We knew the puppeteer was there, this dark matter, because we could see its effects on the puppets. But how do you begin to map a puppeteer you cannot see? You study the dance of the puppets with incredible precision. This foundational mystery, built on decades of indirect evidence, leads us directly to the ingenious tools that finally make the invisible visible. Einstein's theory gave us the key to seeing the unseen. Decades ago, astronomers observed a distant quasar, a brilliant beacon from the edge of the observable universe, but instead of a single point of light, they saw multiple, identical images of it arrayed in the sky. This cosmic mirage was the first stunning confirmation of gravitational lensing, a phenomenon where the gravity of a massive object warps the very fabric of space-time around it, bending the path of light that travels through, just as a glass lens bends light. That foreground object, often a massive cluster of galaxies, acts as a natural magnifying glass. But here is the crucial part for our story. The amount of warping we see is far greater than the visible mass in that cluster can account for. The true lens is the immense, invisible halo of dark matter enveloping it. Every subtle stretch and twist in the light of a background galaxy is a fingerprint left by dark matter's gravity. So astronomers do not look for the dark matter itself. They look at millions of distant, faint galaxies and map the tiny, systematic distortions in their shapes. It is painstaking work, like studying the ripples on the surface of a pond to deduce the shape and size of every unseen stone tossed into the water. This intricate analysis of light allows us to literally weigh the invisible, providing a direct measurement of where the dark matter lies and how much of it there is. It is our first real method for tracing the cosmic skeleton, but to map the entire vast web, we needed to look at the universe in an entirely different way. Light does more than just bend, it also changes color. As our universe expands, it carries galaxies away from each other, stretching the very light they emit. This stretching shifts the light toward the red end of the spectrum, an effect we call redshift. By measuring this redshift for a galaxy, we can calculate its distance from us. Now, imagine doing this not for one galaxy, but for millions. This is the monumental task undertaken by projects like the Sloan Digital Sky Survey, which has spent years systematically scanning the heavens, cataloging the positions and redshifts of countless galaxies. When all these data points are plotted in a vast three-dimensional volume, something breathtaking emerges from the chaos. The galaxies are not scattered randomly. They coalesce into an immense, interconnected architecture, a cosmic web of dense clusters, long, delicate filaments, and vast, empty voids. The galaxies themselves are merely the visible nodes, the glittering ornaments hanging from an invisible Christmas tree. Where you see a dense knot of galaxies, you are looking at a region where the underlying dark matter is most concentrated, its gravity having pulled the luminous matter into its grasp. Conversely, the immense empty voids are not truly empty. They are simply the regions where the dark matter skeleton is at its most diffuse, offering little for normal matter to cling to. Creating this three-dimensional atlas of the cosmos is only the first step. The real challenge lies in using the glitter to deduce the exact shape and strength of the invisible threads holding it all up, a computational puzzle of almost unimaginable scale. This painstakingly assembled map of light gives us the blueprint, but to understand the building itself, we must listen to the universe. To track the evolution of trillions of invisible particles across billions of years is a task far beyond human calculation. This is the monumental challenge that supercomputers are built to solve. Machines like NASA Pleiades, a system with the processing power of hundreds of thousands of laptops combined, run the most sophisticated virtual universes ever conceived. Projects like the Illustris TNG simulation begin with a digital box filled with a primordial soup of particles, representing the state of the cosmos just after the Big Bang. Then they press play. The only rule programmed into this virtual cosmos at the start is the relentless pull of gravity, and from that simple, profound force, something miraculous unfolds. Over eons of simulated time, the dark matter begins to clump and cluster, drawn together by its own gravity, slowly weaving itself into an intricate cosmic web. Filaments form, nodes condense, and vast voids empty out, all within the memory of a machine. This virtual universe in a box is not just a spectacle, it is a fundamental scientific instrument. It allows researchers to run experiments, to ask what if. What if dark matter behaved slightly differently? What if the initial conditions of the universe were changed? By comparing the structure of their simulated cosmic web directly with the observational maps from telescopes, they can test which theories of our universe hold true. The stunning fidelity of these digital realms, their uncanny resemblance to the real cosmos, gives us immense confidence that we are on the right track. It is through this marriage of immense computational power and observational genius that the invisible skeleton of our universe is finally being brought to light. The universe has an original blueprint, and we have a photograph of it. That faint static on an old analog television, the snow between channels, holds a whisper of creation. About 1% of that noise is the cosmic microwave background, the cooled and stretched afterglow of the universe's fiery birth. Space missions like Planck have mapped this relic radiation with such sensitivity that they have created a detailed baby picture of the cosmos when it was just 380,000 years old. This map is not a uniform glow. It is mottled with tiny temperature variations, hotter and colder spots that represent the earliest seeds of structure. These minute ripples in density were the gravitational wells where dark matter first began to pool, the initial concentrations from which the entire cosmic web would eventually crystallize. But the story does not end with this ancient snapshot. As this primordial light traveled for billions of years to reach our telescopes, it passed through the growing cosmic structures of the later universe. When CMB photons climb out of a gravitational well created by a knot of dark matter, they lose a tiny amount of energy, leaving a specific, subtle imprint on the light's polarization. This is the integrated Sachs-Wolf effect, a direct way to trace the shadowy presence of matter that the light passed through on its long journey. It is as if we have a pristine photograph of an empty landscape, and by analyzing the faintest shadows and light distortions on the photo itself, we can deduce the exact shape and location of the giant trees and mountains that later grew there. This ancient light does more than show us the seeds of the cosmic skeleton. It reveals how that skeleton evolved, giving us a unique window into the invisible architecture that defines everything we see. The subtle warp of space-time leaves its signature not in dramatic mirages, but in a collective whisper. This is the domain of weak gravitational lensing, a statistical approach that detects the invisible by its gentle influence on billions of individual lights. Instead of searching for the rare, strongly lensed arcs that create multiple images, astronomers look at the shapes of countless faint, distant galaxies. Each one is minutely distorted, stretched and sheared by an almost imperceptible amount as its light passes through the cosmic web of dark matter. On its own, a single galaxy's slight elliptical shape tells you nothing. It could be inherently misshapen. But when you survey an immense field of the sky containing millions of these galaxies, a pattern emerges. The tiny, coherent alignments of their shapes, all pointing in a similar direction, trace out the gravitational footprint of the massive, invisible structures their light has traveled through. It is like trying to detect a gentle, consistent breeze not by watching a single leaf, but by observing the way an entire field of wheat subtly bends in unison. This statistical power is harnessed by monumental projects like the Dark Energy Survey and the upcoming Euclid mission. These endeavors use wide-field cameras of staggering precision to capture the shapes of billions of galaxies. The data they collect is not a single snapshot of a dramatic lens, but a colossal map of infinitesimal shears. By applying sophisticated statistical analysis to this ocean of data, researchers can perform a kind of cosmic tomography. They can essentially slice through the universe and reconstruct three-dimensional maps of mass itself, revealing the dark matter filaments in stunning detail. The faint statistical signal from any one galaxy is meaningless, but when combined across the vastness of the survey, these whispers become a clear, thundering image of the cosmic skeleton. This monumental task requires more than just a powerful telescope. It demands an unprecedented international collaboration and computing power that can process a deluge of data exceeding the entire text content of the world's libraries. The result is a direct statistical portrait of the invisible, proving that sometimes to see the grandest structures, you must first learn to listen to the quietest signals. High atop a desert mountain in Arizona, a new kind of eye is watching the cosmos. It is not a single lens, but a robotic array of 5,000 tiny fiber optic threads. Each one is an autonomous finger that positions itself with pinpoint accuracy to capture the light of a single, distant galaxy or quasar. This is the Dark Energy Spectroscopic Instrument, DESI, and its mission is to perform a galactic census on a scale we have never before attempted. Over 5 years, it will measure the precise redshift of tens of millions of celestial objects, building a three-dimensional map of the universe so vast and so detailed that it represents a quantum leap in our cartography of the cosmos. We are moving from a rough, hand-drawn sketch of the cosmic skeleton to a high-resolution, satellite-grade image, but this map is not just for looking. Its true power lies in what it can tell us about motion and time. By charting the distribution of galaxies across immense cosmic distances, which also means looking back into deep time, scientists can measure the universe's expansion history with a precision that was once a fantasy. They can track how fast the great filaments and nodes of the cosmic web have grown over billions of years. This growth rate is a direct test of gravity itself on the largest scales, and a powerful probe into the nature of dark energy, the mysterious force accelerating the expansion. Every new galaxy spectrum Daisy captures is another data point in the greatest story ever told, the story of how an invisible skeleton assembled our visible reality and where that entire structure is ultimately headed. Yet the grand cosmic web is defined as much by its threads as by its emptiness. Between the great luminous filaments and clusters lie the voids, immense bubbles of near-nothingness that stretch for hundreds of millions of light-years. These are not simply empty space, they are the actively expanding underdense regions of the universe, the counterpoint to the dense knots of matter. While a cluster is a traffic jam of galaxies pulled together by gravity, a void is a cosmic freeway stretching out, with galaxies slowly drifting away from the center toward the denser walls. This motion is a crucial clue, because gravity is so weak inside these vast empty regions. The growth of a void is not driven by the pull of dark matter, but instead by the push of dark energy. Think of the universe as a rising loaf of raisin bread. The raisins are the galaxy clusters, and the expanding dough between them is the void. By meticulously mapping the shapes and sizes of these voids from galaxy surveys, and by measuring how their expansion has accelerated over cosmic time, scientists get a clean, direct measure of dark energy strength. It is a laboratory with minimal interference where the subtle effects of this mysterious force are easiest to see. These great cosmic deserts, once thought to be mere empty backdrops, are now understood to be active players in the evolution of the cosmos. Their growing silence speaks volumes about the forces shaping our ultimate fate. Those primordial pressure waves left a permanent scar on the cosmos. In the universe's first hot, dense moments, it was not a calm sea but a raging cauldron of plasma, a fluid of particles and light. Within this soup, pressure waves surged outward, much like sound waves moving through air. These were the Baryonic acoustic oscillations, ripples of compression and rarefaction that traveled at a significant fraction of the speed of light. But this furious activity could not last forever. When the universe cooled enough for atoms to form, a moment we call recombination, the music suddenly stopped. The waves froze in place, their progress halted, leaving a single, characteristic scale imprinted on the distribution of matter. Think of it like a pond that instantly turns to solid ice, capturing the exact size and shape of every ripple on its surface at that single moment. This fossilized ripple, this standard ruler, became a permanent part of the cosmic skeleton. Today, when we look at the vast three-dimensional maps from instruments like Daisy, we can still see this ancient signature. Galaxies have a subtle, statistical preference to be separated by a specific distance, about 500 million light-years. That is the size of that primordial ripple, stretched to a colossal scale by the expansion of the universe over billions of years. This 500 million light-year rule is our golden measuring stick. By observing how this standard ruler appears to our telescopes at different epochs, at different distances, and thus different looks back into time, we can measure the expansion history of the universe with breathtaking precision. It is as if we had embedded a ruler with a known length into the fabric of space itself at the moment of creation, allowing us to see exactly how much that fabric has stretched between then and now. This single, subtle pattern, a ghostly echo from the universe's first moments, provides one of the most powerful and direct tests we have for understanding the dark energy that drives our cosmic fate. No single map of the cosmos is flawless on its own. Each observation, from the subtle warping of light to the ancient glow of the cosmic microwave background, carries its own unique set of uncertainties and potential blind spots. The true breakthrough in modern cosmology comes not from relying on one method, but from weaving them all together. This powerful technique is known as cross-correlation, a statistical process that merges different cosmic maps to reveal a clearer, more confident picture of the invisible. Imagine you have a faint, blurry photograph of a city at night showing only the brightest streetlights. Then you get a thermal image of the same city, showing the heat signatures of buildings and power lines. Individually, each image is hard to interpret, but when you overlay them perfectly, the bright lights align with the warm buildings, and suddenly, the entire urban structure makes sense. This is what scientists do with the universe. They take the map of galaxy positions from a massive redshift survey and lay it over the map of mass distribution derived from weak gravitational lensing. When the peaks of inferred dark matter density align perfectly with the dense knots of galaxies, the conclusion becomes undeniable. The skeleton and the luminous body are in the same place. This multi-messenger approach extends even further, cross-referencing these findings with the primordial blueprint of the cosmic microwave background. The subtle imprints left on that ancient light by the evolving cosmic web should, and do, match the structures we see forming in the galaxy surveys. Each independent line of evidence acts as a cross-check on the others, cancelling out individual biases and shrinking the margins of error. This grand synthesis of data is pushing the very frontiers of statistical analysis, demanding immense computational power to reconcile terabytes of information from telescopes around the world and in space. The result is a portrait of the dark cosmos we can finally trust, a map where the invisible lines are drawn not in pencil, but in ink. A profound crack has appeared in the foundation of modern cosmology. We call it the Hubble Tension, and it is a discrepancy that refuses to go away. Measurements of the universe's current expansion rate, taken from nearby stars and galaxies, consistently return a faster, more frantic value than the rate predicted by studying the ancient afterglow of the Big Bang. It is as if we have two clocks for the cosmos, one set in the primordial past and one ticking in the present, and they are stubbornly out of sync. The growth of the cosmic web is inextricably linked to this expansion speed. The rate at which dark matter filaments condense and galaxy clusters assemble is choreographed by the underlying tempo of the universe's stretching. This is where our maps of the invisible skeleton become a crucial arbiter. By measuring the exact size and maturity of the Webb structures, we gain an independent third way to measure the Hubble constant. We are no longer just looking at the expansion itself, but at its consequence, the architecture it has built over billions of years. If the cosmic skeleton appears more fully formed, with thicker filaments and denser nodes than the standard model predicts, it would be a powerful vote for the faster, modern expansion rate. Such a finding would be more than a simple adjustment. It would signal a fundamental flaw in our understanding. The tension is not an error, it is a clue. It hints at the possibility of exotic new physics, perhaps a previously unknown form of dark energy that changed its strength over time, or a strange property of dark matter itself. Mapping the skeleton has become the ultimate test, a way to see if the very laws we use to describe the cosmos are complete. or if we are on the verge of a revolution as profound as the discovery of dark matter itself. The sheer volume of data is itself a cosmic frontier. These surveys generate not just images but petabytes of information, a number so vast it dwarfs the entire printed collection of the world's libraries. No team of humans could ever sift through this digital ocean to find the subtle patterns we seek. This is where a new kind of intelligence enters the story. Machine learning algorithms trained not on human language but on the virtual universes created by supercomputers are learning to see the invisible. They are given millions of simulated images of the sky, complete with realistic galaxy shapes and the known underlying dark matter distribution that caused them. The algorithm's task is to learn the relationship, to understand how a specific pattern of gravitational shearing in the light of galaxies corresponds to a specific configuration of dark matter filaments. Once trained, these neural networks are unleashed on the real telescope data. They can identify the faint, telltale signs of weak gravitational lensing with a reliability and speed that human-written code simply cannot match. They classify galaxy shapes not just with superhuman accuracy, but with a consistency that removes human bias from the equation. Think of it as teaching a master cartographer the fundamental principles of geography and then giving them a satellite image of an entire, uncharted continent. The algorithm does not get tired, it does not miss details, and it can process a continent's worth of data in the time it takes us to blink. These artificial intelligence systems are the indispensable translators, turning the raw, noisy cacophony of telescope pixels into the clean, precise maps of the cosmic skeleton. They are accelerating our journey from mere data collection to genuine, profound insight, learning the silent language of gravity to draw the universe's hidden blueprints. The sheer ambition of this new endeavor is almost beyond comprehension. For 10 years, a single telescope will perform the most comprehensive celestial inventory ever attempted. The Vera Rubin Observatory's Legacy Survey of Space and Time, or LSST, will not simply take pictures of the sky, it will capture it in motion. Its massive camera, the largest digital eye ever built, will photograph the entire available southern sky every few nights, repeating this cycle for an entire decade. The result will not be a static atlas, but a cosmic movie, a time-lapse of the universe on a scale we have never before witnessed. Every patch of darkness will be revisited again and again, revealing subtle changes. This relentless observation is the key to its primary mission, to unravel the mysteries of dark matter and dark energy. By applying the principles of weak gravitational lensing to this unimaginably vast dataset, the LSST will trace the invisible skeleton with a clarity that makes our current maps seem like rough sketches. It will track the slow, gravitational choreography of the cosmic web in real time, watching as filaments thicken and stretch, and as voids grow ever larger and emptier. We will see the architecture of the cosmos not as a finished building, but as a living, breathing entity under construction. This dynamic view is crucial because it is in the motion, in the evolution, that the true nature of dark energy reveals itself. The LSST will measure the accelerating expansion of the universe not as a single number, but as a detailed history, showing us if the push of dark energy has remained constant or changed over billions of years. The anticipation for this flood of data is already reshaping cosmology, forcing us to build new tools and new theories to comprehend the revelations to come. We are on the verge of turning the universe itself into a documentary, and we have front-row seats to the greatest show in the cosmos. Yet for all our detailed mapping, we still do not know what the cosmic skeleton is actually made of. Its fundamental nature remains one of the deepest puzzles in all of physics. Is dark matter a sea of cold, slow-moving particles that barely interact with anything, even themselves? This is the leading idea known as cold dark matter, and it forms the bedrock of our standard model of the cosmos. Or could it be something else entirely? Perhaps dark matter is warm, moving at a significant fraction of light speed, which would prevent it from clumping on the smallest scales. Maybe it even possesses a hidden force, allowing it to interact and collide in ways we have not yet imagined. The answers to these questions are not written in the stars, but in the precise architecture of the cosmic web itself. The very shape of the filaments and the number of small, dwarf galaxies orbiting larger ones serve as a cosmic laboratory. Cold dark matter predicts a universe that is fundamentally lumpy on every scale, filled with a vast population of tiny dark matter clumps and dense, intricate filaments. If we could zoom in on a filament, it should look like a dense rope woven from countless smaller strands. Alternative theories like warm dark matter predict a smoother, more streamlined cosmic web with fewer of these tiny clumps and more diffuse filaments. It is the difference between a river delta, choked with countless small islands and muddy tributaries, and a single, clean, fast-flowing channel. Every time our surveys fail to find a predicted dwarf galaxy, or every time we measure the exact thickness of a filament spanning the void, we are conducting a fundamental experiment on the properties of dark matter. We are not just drawing a map, we are running a diagnostic test on the most abundant form of matter in the universe, using the cosmos itself as our experimental apparatus. The silent, invisible threads of the cosmic web are whispering their secrets, and we are finally learning how to listen. While our cosmic maps reveal the grand architecture of dark matter, they cannot tell us what it is made of. This question drives a parallel quest, one that descends deep beneath the Earth's surface. To have any hope of detecting a hypothetical dark matter particle, scientists must escape the constant rain of distracting cosmic radiation. Laboratories are built within mountains or in old mines, where thousands of feet of solid rock act as a natural shield. In these pristine, silent caverns, experiments like LUX Zeppelin and Xeno NNT wait in the darkness. Their core is a vat of ultra-pure liquid xenon, a medium so sensitive that it might register the unimaginably rare kick from a dark matter particle striking a xenon atom. It would be a collision more subtle than a whisper, a tiny burst of light and charge that would signal the first direct contact with the cosmic skeleton. After years of searching, these detectors have seen nothing but background noise, yet their increasing sensitivity steadily closes the door on what dark matter cannot be, guiding us toward what it might be. The search also extends into orbit. Attached to the International Space Station, the Alpha Magnetic Spectrometer sifts through the torrent of cosmic rays, searching for an unexpected excess of positrons, the antimatter counterpart to electrons. Such a signal could be the smoking gun of dark matter annihilations, the faint echo of particles colliding and destroying each other in the void of space. A single, confirmed detection in any of these experiments would be transformative. Knowing the particle's mass and how it interacts would immediately answer why the cosmic web formed with the specific texture we observe in our maps. The immense gravitational dance of galaxies and the silent, patient hunt in an underground tank are two sides of the same profound investigation. The universe's largest structures and its smallest possible particles are inextricably linked, and the final answer will require listening to both. This relentless push from dark energy is actively reshaping the cosmic architecture. While dark matter's gravity works tirelessly to pull the universe together, weaving filaments and condensing clusters, dark energy exerts a countervailing pressure, stretching the very fabric of space and making it increasingly difficult for new structures to form. It is a cosmic tug-of-war unfolding over billions of years, and the cosmic web is the visible, or rather invisible, record of that struggle. In the early universe, gravity held the upper hand. Dark matter coalesced, drawing in normal matter to build the first galaxies and the great filaments that connect them. But as the universe grew older and more diffuse, the influence of dark energy began to dominate. Its repulsive effect acts as a sort of cosmic resistance, slowing the growth of the skeleton. Think of it like trying to build a sandcastle as the tide is coming in. You can still pile the sand, but the incoming waves make it harder to add new layers and eventually begin to erode what you have already built. In our universe, the tide of dark energy is rising. We see this in the maps. The great filaments are not just sitting there, they are being stretched, becoming thinner and less dense over time. The formation of new, massive galaxy clusters has significantly slowed. The universe is moving from a period of intense construction to a gradual, accelerating dissolution. This is why measuring the precise rate of this cosmic slowdown is so critical. By comparing the richness of the cosmic web in the distant past, seen in deep surveys, to its structure in the more recent universe, instruments like the Dark Energy Survey and the Euclid Space Telescope can measure the strength of dark energy's push across cosmic history. Is this force a true constant, an immutable property of space itself, as Einstein once proposed, or does its strength wax or wane over time? The answer is written in the thinning threads of the cosmic skeleton. The ultimate fate of everything, whether the web will eventually be pulled apart into isolated islands of galaxies or persist in a diluted form, hinges on the outcome of this silent, pervasive battle between the pull of the dark and the push of the void. The ancient infrared sky holds secrets of creation itself, and we finally have the tool to pry them loose. The James Webb Space Telescope, orbiting 1,000,000 miles from Earth, is our most powerful time machine, its golden eye tuned to the faint heat glow of the universe's first starlight. While other telescopes map the mature cosmic web, Webb peers back to its very birth, to an era just a few 100 million years after the Big Bang, when the first galaxies were igniting. The question is not just when they formed, but where. Did these infant galaxies light up at random, scattered like lone campfires in a vast wilderness? Or were they already aligned, strung like beads along the invisible, primordial threads of the dark matter web? Webb's incredible sensitivity to infrared light allows it to see the answer. The expansion of the universe has stretched the ultraviolet light from those first stars deep into the infrared part of the spectrum, a domain where Webb is king. It is collecting the faint photons that have been traveling for over 13 billion years, showing us the universe not in its maturity, but in its infancy. And what it reveals is astonishing. The earliest galaxies are not scattered randomly. They are already clustered, already forming chains and protofilaments that align perfectly with the predictions of our dark matter models. It is like finding the foundations of ancient Roman roads, long buried, and realizing they were built along even older, invisible pathways. These are the first wisps of the cosmic skeleton, the dark matter filaments beginning to pull matter together, creating the gravitational wells where the very first stars could be born. Every deep field image from Webb is a test. Does the distribution of these primordial galaxies match what our supercomputer simulations predicted for the early universe? So far, the answer is a resounding yes, but with intriguing twists. Some galaxies appear too massive too soon, challenging our models of how quickly structure could form. This is not a failure, it is a refinement, forcing us to sharpen our understanding of how the invisible skeleton assembled the very first pieces of the visible cosmos. Webb is giving us a front row seat to the universe's first construction project, watching as the dark matter framework, laid down in the first moments, begins to be decorated with the glitter of its first cities. The cosmos contains another ghost, one that flows through you by the trillions every second. These are neutrinos, subatomic particles so elusive they were once thought to have no mass at all. Born in the inferno of the Big Bang, a cosmic sea of these relics now permeates every cubic inch of the universe, a background fog of reality as fundamental as the cosmic microwave radiation. For the cosmic web, their influence is subtle but profound. In the universe's first moments, these neutrinos were searingly hot, moving at almost the speed of light. This incredible velocity gave them a unique property. They could not be trapped by the small, initial gravitational wells of dark matter. While cold dark matter was clumping together to build the foundations of the cosmic skeleton, these hot neutrinos were streaming outward, their energy acting like a gentle pressure that smoothed over the smallest wrinkles in the fabric of space. Think of it like trying to build a delicate sandcastle while a constant, faint breeze blows across the beach. The breeze does not destroy the castle, but it erases the finest details, the tiniest peaks and valleys you try to form. This is the neutrino effect on the cosmos. It suppresses the formation of the very smallest clumps of dark matter. The consequence is a cosmic web with slightly thinner filaments and fewer tiny, dwarf galaxies than we would expect if dark matter were working alone. This ghostly signature is imprinted in two key places: the large-scale distribution of galaxies we map with surveys like DAISY, and the subtle patterns of gravitational lensing we see in the cosmic microwave background. Finding this faint statistical signal is one of the most difficult challenges in modern cosmology, a search for a whisper within a whisper, yet the prize is immense. Because the strength of this smoothing effect depends directly on the mass of the neutrino, successfully detecting it would give us our first direct measurement of the absolute mass scale for these phantom particles. It would be a fundamental discovery achieved not in an underground lab, but by reading the grand architecture of the universe itself. Our maps of the invisible skeleton are therefore more than just charts of dark matter. They are a complex ledger where the gravity of the cold, dark cosmos is meticulously balanced against the fading pressure of its oldest, fastest ghosts. But what if the entire premise is wrong? What if there is no dark matter at all, and the invisible skeleton is just a phantom, a symptom of our own misunderstanding? A small but persistent group of physicists argues exactly that. They propose that our theory of gravity itself is incomplete. Einstein's general relativity, so successful in describing the solar system and black holes, might break down on the vast, diffuse scales of galaxies and beyond. Their alternative is known as modified Newtonian dynamics, or MUND. This idea suggests that the force of gravity does not fade as quickly over immense distances as our current laws predict. This extra gravitational tug, they argue, is what holds spinning galaxies together without needing any extra invisible matter. It is an elegant solution, removing the need for a mysterious substance that has eluded direct detection for decades. Yet this elegant idea faces a brutal reality check in the form of the cosmic web, and one cosmic collision in particular. The bullet cluster is a system of two galaxy clusters that have violently smashed through one another. When we map this region, we see something that is very difficult for modified gravity to explain. The visible, hot gas from the clusters, detected by its X-ray emission, was slowed down by the collision and sits in the middle. But the bulk of the mass, mapped through gravitational lensing, has sailed right through and now resides in two large clumps, completely separated from the visible matter. This is a direct image of dark matter behaving exactly as a separate, collisionless substance would. It is as if two crowds of people ran into each other, but their shadows kept walking forward, detached from their owners. No simple modification of gravity can easily account for why the gravitational field is not centered on the visible stuff. The existence of this separated mass is a profound challenge. The intricate, web-like structure of the universe itself, with its specific patterns of filaments and voids, becomes the ultimate testing ground. Can any tweak to the law of gravity successfully simulate the evolution of the entire cosmos, from the smooth early universe to the complex cosmic web we see today? So far, no modified gravity theory has managed to replicate the stunningly accurate structures produced in supercomputer simulations that include dark matter. The maps we are creating are more than just charts. They are the final arbiter in a fundamental debate about the very laws of physics. They force us to ask whether we are missing a fundamental component of the universe, or whether we must rewrite the rules of gravity that have guided our understanding for a century. These scientific maps have blossomed into a new art form, a visual poetry of the invisible. You have likely seen these renderings, breathtaking digital sculptures of a universe woven from luminous threads against the profound black of space. These are not direct photographs, but powerful translations where scientific data is given color and form. An artist might take a supercomputer's three-dimensional map of dark matter density and turn it into a brilliant, intricate network of glowing fibers, with sparkling galaxies nestled at the intersections. These visualizations do more than just illustrate a theory. They make the abstract real for millions of people. They transform columns of numbers and statistical correlations into something we can see, feel, and intuitively grasp. It is the difference between describing the structure of a snowflake and holding a perfect, crystalline example in the palm of your hand. This act of translation is a profound public service. When a child looks at a visualization of the cosmic web and understands that our galaxy is a single speck on a vast, invisible bridge, it ignites a sense of wonder that a textbook equation never could. These images are the gateway, inviting everyone to ponder the same mysteries that captivate the world's leading physicists. They answer the fundamental human need to visualize our reality, to see the hidden architecture that cradles our existence. This cultural impact is not a secondary benefit, it is essential. Public fascination and support are the lifeblood of the monumental projects that drive this science forward. The stunning images that grace magazine covers and documentaries are a vital feedback loop, generating the excitement and political will that fund the next great telescope, the next ambitious sky survey. By giving a visible form to the dark cosmos, scientists and artists together are weaving this profound knowledge into the very fabric of our culture, reminding us all that we live in a universe far grander and more mysterious than our eyes alone can ever reveal. Such monumental projects demand a monumental investment of human and financial resources. The Vera Rubin Observatory and the Euclid Space Telescope are not solitary endeavors. They are global enterprises involving thousands of scientists, engineers, and technicians, funded by nations pooling their wealth and expertise for decades. This scale of big science inevitably raises profound questions. In a world with so many pressing needs, how do we justify the billions spent to map an invisible cosmic skeleton? The answer lies in a fundamental human value, the pursuit of knowledge for its own sake. These projects are a testament to our innate curiosity, a modern incarnation of the same drive that led explorers to cross oceans and gaze at the stars. They ask not what this knowledge can build or buy today, but what it reveals about our place in the cosmos. This philosophical stance is woven into the very fabric of these missions through a powerful principle: open data. After a proprietary period for the core teams, the torrents of data collected are released to the entire world. freely accessible to a university student in Chile as to a professor in Tokyo. This creates a truly global scientific community, breaking down barriers and ensuring that the quest to understand the universe is a collaborative and not a competitive human enterprise. It transforms the data from a proprietary asset into a shared inheritance. This raises another critical question: who owns the blueprint of the cosmos? The ethical consensus is that no single nation or institution can claim it. The data is a common resource, a map of a reality that belongs to everyone and no one. This grand collaboration is more than a logistical necessity. It is a profound choice. It reflects a collective decision to allocate a portion of our civilization's energy to answering the most fundamental questions we can ask. Why does anything exist? What is the universe made of? How did it begin and how will it end? The act of building these cosmic cartographers is itself a reflection on who we are, a species that chooses to look up and invest its finest efforts into understanding the vast, dark, and beautiful architecture we call home. The cosmic cartography we have today will soon look like a child's first drawing. Our next great observatories are already on the drawing board, designed to push our vision of the invisible into realms of unimaginable precision. The NASA Nancy Grace Roman Space Telescope, for instance, will conduct a weak lensing survey so vast and detailed it will dwarf all our previous efforts combined. Its wide field view will measure the shapes of billions of galaxies with a surgeon's accuracy, tracing the subtle shears caused by dark matter with a clarity that could reveal the texture of individual filaments. We will no longer just see the skeleton, we will be able to study its musculature and tendons, but our ambition reaches even further back in time, to the very instant of creation. Future concepts for cosmic microwave background experiments aim to capture the faintest whisper in the universe's oldest light, a specific pattern of polarization imprinted by primordial gravitational waves. These waves would be ripples in space-time itself, generated in the first chaotic fraction of a second after the Big Bang. Detecting this signal would be like finding the original architectural plans for the cosmic web, showing us the exact tremors that shaped the distribution of all matter to come. This is not just about mapping what is there, it is about understanding why it is there. The ultimate objective, the holy grail of this entire endeavor, is a four-dimensional map of the dark cosmos. Imagine a celestial atlas where you could not only fly through the three-dimensional structure of the filaments and voids, but also slide a cursor through billions of years of cosmic history. You could watch a single dark matter filament condense from a faint wisp, grow to maturity, and then slowly stretch and thin under the influence of dark energy. We are transitioning from an age of simply discovering the skeleton to an age of precision cosmology, where we understand its growth, its metabolism, and its ultimate fate. The revelations of the next decade will not just add details to our maps, they will fundamentally redefine our cosmic address, telling us not just where we are in space, but precisely where we stand in the epic life story of the universe. Our entire world exists on a tiny fragment of a single thread in the cosmic tapestry. This Milky Way galaxy of ours, with its hundreds of billions of stars, is not a solitary island but a traveler on an immense, invisible bridge of dark matter, one filament among countless others in the sprawling web. This realization is more than just a scientific fact, it is a profound philosophical shift. The same gravitational rules that orchestrate the spin of a galaxy and the slow dance of these billion light-year filaments also govern the fall of an apple from a tree. The carbon, oxygen, and iron that make up our bodies were forged in the hearts of long-dead stars, stars that themselves could only form within the dense gravitational wells provided by the dark matter skeleton. We are not merely living in the universe, we are a product of its most fundamental architecture. We are the universe become conscious, a way for the cosmos to look back at itself and begin to understand its own hidden structure. This quest to map the invisible is at its heart a search for our own cosmic ancestry. It challenges the deeply ingrained notion that we are at the center of everything, revealing instead that we inhabit an unremarkable neighborhood in an unimaginably vast and mostly dark metropolis. We have journeyed from the first puzzling clues of spinning galaxies through the cosmic mirages of gravitational lensing to the supercomputer simulations that breathe life into the dark cosmos. We have seen how ancient light and modern telescopes work in concert to trace the ghostly outlines of the filaments and voids. This is not just a story of mapping darkness, but of illuminating our own place within an epic narrative. We are connected to the largest structures in existence by the very atoms in our bodies and the physical laws we have deduced. To understand the cosmic web is to finally read the story of how everything, including us, came to be. This journey through the dark cosmos reveals a profound truth. We are living in a golden age of cosmic revelation. From the first puzzling clues in spinning galaxies to the statistical whispers of weak gravitational lensing, we have assembled a toolkit of unprecedented power. We are no longer just inferring the invisible skeleton, we are tracing its filaments with precision, weighing its nodes, and watching it evolve across time. This entire endeavor stands as a testament to human curiosity and collaboration, uniting telescopes in space, supercomputers on the ground, and the minds of thousands across the globe. It pushes the very limits of our knowledge, challenging the laws of physics as we know them, and probing the mysterious dual nature of dark matter and dark energy. Every new data point, every refined map, is not an end but a beginning, a step closer to answering the most fundamental questions of our existence. Why is the universe structured this way, and what is our true place within its vast, invisible architecture? Let this exploration be a starting point for your own wonder. If unraveling the secrets of the dark cosmos captivated you, consider subscribing for more journeys to the edge of our understanding. We would love to hear which cosmic revelation struck you most deeply, so share your thoughts in the comments below.